Did you know there's a type of star that's held up entirely by quantum effects? I'm going to tell you all about it because they're so cool. So, right, this here is our sun. Having a lovely time, shining brightly, we're all very proud, everyone say thank you sun. Inside the sun we have a lot of fusion going on that's moving things from hydrogen to helium, and then you get from like helium to the carbon, the oxygen, and it's the energy released from that that stops the star from collapsing in on itself. So stars are just constant battles where we have gravity pulling everything in, and then on the inside we have all of this fusion going on that is releasing radiant energy that's kind of pushing out against that. Now, the reason why fusion actually releases energy is because of something called the binding energy. Basically, the higher up your binding energy, the more stable you are, because it's like the amount of energy you'd need to break apart that atom. So when we go from hydrogen to helium in a star through fusion, the helium has a higher binding energy, and basically what that means is less energy is needed to keep it together, which means that when we go from this to this, there's a little bit of energy left over. And by the law of the conservation of energy, that's got to go somewhere, and so it's let out in the star. As you move from the light elements, so here we have hydrogen, then we go up helium, carbon, oxygen, eventually you hit iron. Everything above iron, the binding energy starts going down again. So this is why when we do fission, which is the other way, we go from big elements to smaller ones, we get a release in energy as well, because we're moving up in the binding energy. So as the stars age, they go up through all these elements. Eventually they run out of hydrogen, they start to fuse helium, and then all the carbon, oxygen, blah, blah, blah. Eventually, in the core of the star, they make iron. And that is the death toll for the star. Suddenly, this fight becomes a lot more one-sided. So when this happens, the core of the star gets crushed in really, really tight, and then all the kind of gas that was on the outside, that tends to start drifting away as everything loses cohesion. These are called planetary nebulas, and they are so pretty. But what about that core? What happens to that as everything is crushing in? Now here we're talking about lighter stars, heavier ones become neutron stars or black holes, but these become white dwarfs. And this is where the quantum weirdness comes in. Now, if we imagine we have a particle, what quantum mechanics tells us is that it has some uncertainty in its position and momentum. So this is called the Heisenberg uncertainty principle. So instead of being this discrete point, it's more like a cloud where the point could be. And to further confuse things, we have the Pauli exclusion principle, which basically says no two quantum particles can share the same state. Basically means these clouds of particles will not be able to push in, which gives us what we call the electron degeneracy pressure, where the quantum effects of the fact that electrons cannot be squeezed any closer together pushes back against the gravity of the star, and that gives us a white dwarf. I just think that's really cool. If you have any other star questions, let me know, because I love talking about stars. Okay, have a lovely day. Okay, bye.